lecture 1, topics in applied optimization. There will be some theory and some applications, a bit more theory than applications, but there will be quite a few applications. Okay, since this is an optimization course, you will see a lot of optimization theory here. So let us see what to expect. Okay, so in the first lecture, I will give you some overview, and then maybe I can already start with the review thing. Okay, so let us see. So course information. So the name of the course, the code, and all this is known by now. Okay, prerequisite for this course are basic linear algebra, but this is something I will review. Actually, I plan to start it today itself. So I will go through the basics, matrices, vectors, and some of the basic results, and so on. So this will give you some opportunity to review. And multivariable calculus is something we will need. Concepts of gradients, Hessian, and a bit about matrix calculus. Okay. This is also something I plan to review in the beginning. So first two classes will be review. Basic probability and statistics. Again, this will be review. Probability and statistics will be not much. Okay, very little. I mean, maybe two classes will need probability and statistics type. And then I'm expecting that you have familiarity with C, C++, okay, Python, MATLAB. Well, MATLAB is very easy. In case I do in some code, MATLAB code, you should not be too afraid. It's very simple. Okay. I request that all of you turn off your microphone unless you are going to speak. Okay. Otherwise, I hear the noise. Okay. Okay. When you are going to speak, of course, you can turn on the microphone. If you want to share some handwritten thing or something in the chat box, then you let me know. Okay, then I can see. Okay. Okay, so these are the prerequisite. Okay. It may look like there are quite a few, but as I said, basic stuff are needed from here. Some part you don't need to know everything. Yeah, usual Linux utilities, because you may have to work with on command line stuff, especially if you have to do the coding. Okay, so there is some amount of coding in this course. Okay. Weightages, online randomized quizzes will be there since we are doing online teaching. You will have a good amount of online quizzes. Okay, these quizzes can be surprise quiz. So while you are doing the class, at some point I may say that, okay, let us have a quick quiz, and this quiz can be like 1 question, 2 question, something like that, 3 question, conceptual questions, and that will test whether you are following the code, and this will be graded. Okay, so there will be marks for these online quizzes. This will also take into account that most of you are attending most of the quizzes. Okay, I can give you, let us say, the best of. Let us say there are 15 quizzes. Then maybe I can say you can go with best of 10. Okay, best 10 you can choose. So in some cases you may miss some quizzes, or maybe you are not attending class for some reason. So that's why I can give you something like that. I have not thought about it, but these surprise quizzes will be graded. Okay, and there will be grading for that. You are allowed to miss some. Okay, and obviously you cannot do this offline, right? So you cannot say that, oh, I missed the classes, so I cannot give the quiz. So, but then those quiz marks won't be like, you won't get those marks, right? So these are the things with the consequence of online thing, and you will have online written exam. So that will be 20%. Let's say I plan to do only ANSEM. So it will be like 30 minutes written exam or 45 minutes written exam. Okay. These quizzes, as I say, I can be randomized. Okay, even the surprise quizzes I'm asking you can have randomized values in the question, randomized values in the answer. So depending on like what you see, right? So it may differ. The choices may differ. Projects will be there in this course. There's a tradition in this course that people do end up doing a good amount of project. So that will contribute 25%. So projects are usually you are given some paper or some report, okay, and then you are supposed to do the coding, and then you also have to do the presentation. Okay, here the focus is on the optimization part. Okay, so how are you going to implement the optimization methods? There will be assignments that will be also 25%. Okay, so this is take home assignment. So again, you will be given some code, but the part where optimization is needed, that will be left for you to fill. So how do you model a problem? How do you solve it? Okay, so those things will be the assignment. The references, there could be quite a few references here. I'm not saying that only one book is there, but there is one main book that you can have, and this is a free book, online book. The first reference, Convex Optimization by Boyd and Vanderberge. So this is the main textbook. You will see that roughly 50% of the material that I will cover can be found here. Okay, so this is the convex optimization part. There is also another book by Bert Sekas. So here also you have the similar material as the Boyd and Vanderberge. Okay, but this second reference is a little bit sometimes not so trivial to follow. Okay, so in that case you may prefer to use the Boyd book. Okay, that is more, that explains a little bit more. We may need to follow, I mean, we will follow some optimization models in that is found in deep learning and so on. I will let you know what exactly I'm talking about. You don't need to know deep learning, as I said. All the necessary thing will be told to you. Okay, so numerical optimization is another book. It is also a pretty standard book. Some few things can be taken from here. Okay, and there is a non-convex optimization, which is by Jan. So this guy is in Microsoft Bangalore. So he has written a nice report on focusing on non-convex optimization. Okay, so non-convex optimization is also very much there. In fact, deep learning is a non-convex optimization problem. Okay, in deep learning. So that's the interest in this area is pretty high. Okay, because the deep learning interest is pretty high. Non-smooth optimization. Okay, so non-smooth optimization is also something we will see. I'm not going to define it right now. Okay, I mean, very shortly, it's like even the function that you are going to minimize is not smooth. By that we mean not differentiable. Okay, I mean, the reason why it matters is that most of the algorithms that you tend to follow is a gradient based method. Okay, and gradient is a derivative, right? So if a function is not smooth, then technically speaking, you cannot compute the derivative, and that's why that's the problem. Okay, if a derivative is not well defined, right? At a corner point, the derivative is not well defined, right? So it's the non-smooth problems are like that, right? So I have something like this, and then I have this mod x function, right? So derivative here is not really defined, right? So fx is absolute value of x. At 0, the derivative is not defined in the sense that there is no unique tangent, right? You have multiple tangents here, right? So you have this is also a valid tangent. Okay, this is also a valid tangent. This is also a valid tangent. So this is the issue here. Like there are infinitely many tangents with the tangent values going from -1 to 1, right? So it's like so many slopes are possible here. So this is the problem, okay? So and gradient methods require you to compute the gradient, okay? So you need gradient of f of x. But then like how will you compute? Like you have so many possibilities for a tangent, like which one to choose, right? Anyway, we will discuss these things in detail. I'm going ahead of. So, and even convex, non-convex, you may not know by now. So I have not explained this anyway. Like I tried to explain you this, but even these things have to be well defined, right? So all this we will see in detail. Okay. So these are the broad topics, and inside you will see many things that will show up. So some remarks: attendance is not necessarily compulsory, but then, as I said, to maintain a decent interaction, there will be surprise quizzes that will require you to attend most of the classes. Okay, as I said, you can if you miss some classes, then you are missing those quizzes as well, and then you have liberty to lose some, because only some of the best scores of your quiz will be taken into account in the final grading. Okay, so there will be surprise quizzes, and these quizzes, since we are in the online mode, this is a good way for me to judge you, because you have seen a lecture and then I can immediately see, okay, whether, and these quizzes will be more a conceptual thing. So it will be more about whether you are following the basic things and so on. And this will give you an immediate feedback to see, to revise if it is needed. Okay, so yeah, so as I said, it's highly recommended to attend classes because quizzes are there sometimes, and these quizzes depend on what I might have discussed. Sometimes I might say things orally, and quiz will be based on that. Okay, so if you are attending, then you will remember these things. Linear algebra, advanced calculus. By advanced, it's not really advanced calculus. By advanced calculus, I mean concepts of gradients, Hessian, taking derivative of a multivariate function, right? So that's the gradient, Hessian, and so on. And what are the chain rule and so on. Depending on whom you ask, whether it's advanced or not, we can argue, right? So we will see those things anyway, how to compute these things. Prob and stat, as I said, maybe 2 classes we will need that. Okay, so I will let you know the details of that. Previous knowledge of machine learning is not necessary because our focus is on the optimization part. So we will choose some basic machine learning models as a template. Okay, and the questions will be always on the optimization, not on the machine learning part. Okay, some of the applications we plan to cover will be, as I said, the regression problems, classification problems. Okay, so usual neural networks, as I said, are non-convex and non-linear. Okay, so these are non-convex and non-linear. Okay, so that's already a big problem here in hand. SVMs usually are convex, but they are constrained optimization problem. Artificial neural networks are usually unconstrained. Okay, I will explain what I mean by unconstrained and constrained. Okay, so don't worry about that. And we will see some application of optimizations in the generative models. For example, let us say GANs, okay, generative adversarial model networks. And here, so each of them bring some different flavor to the optimization problem that you need to look at. For instance, GAN is a min-max problem. It's just not it is not just min or max, right? So usual optimization problem you can think of minimize something, okay, subject to some constraint. Okay, so this is the typical minimization problem, but GANs are not just like that. Okay, GANs are mean as well as max. So it's like simultaneous mean max, simultaneous. Okay, it's not like sequential. You can say first mean and then max. No, because okay, let me because it's like more variable case, right? So you have x, y. So someone is telling you to minimize this with x and then maximize this with y. Okay, if you do it sequentially, like let me minimize f of xy with x first and then maximize with y first, that doesn't always work. Okay, it's a simultaneous min max problem, or max min or min max. Okay. Okay, and min max min can be changed to min max just by changing f to minus f, right? So if I change f to minus x, then this is same thing as saying max of this and mean of that. So min max mean same thing. Minimum similar in the same spirit. Mean problem is the same as the max of mean of f of x is same as the max of minus of f of x. Okay, so you will see that we will not really distinguish between mean and max. So both are same thing. It's like doing mean of my negative or okay. So you get the point. So GANs give you a different type of optimization problem to solve. Okay, so there is a generator, there is a discriminator, and then both one is trying to minimize and one is trying to maximize the score and so on. Okay, so we will see these things in detail. So min max problems are more like a two-player game. You can formulate this as like a two-player min max game. We will see this is in detail. Okay, so it's like you kind of looking for some kind of an equilibrium. Okay, you cannot satisfy both mean and max, but you may agree to settle on certain point, certain values of x and y, for which you say that okay, it's fine, it's you accept that. Okay. Okay, so then we will see some recommender systems. So recommender system, for instance, let us say movie recommendation system, right? So that is again a optimization problem is everywhere. That's what I'm trying to say here. Okay, in all machine learning problem, you are trying to find a better model, and this better model is found by minimizing some loss function. Okay, so and you are minimizing over the parameters of your model, and once you have minimized, your model has learned. Okay, and so this is why all the machine learning models need optimization solver. Okay, modeling is the important part. How you model your problem, that's already is a very big deal. So someone asks you, okay, show me a recommender system. I want to build a recommender system, right? So now the first step you have to think is what is the model? What is the model, right? So, and the model will turn out to be some kind of an optimization model, right? You will think about some loss function, right? So that's your objective. And then you have to minimize, okay? And this loss is defined over what? Okay, whether it's a shallow network like SVM or deep neural networks, or whether it's some kind of a GAN setting, right? It's whether it's a recommended system type setting. So modeling is one part, how you model your problem as optimization problem. And then once you have that, then how you solve that. Okay, so both these things we have to see. Okay, and we will see some additional things from, let us say, computer vision. You don't need to know computer vision. As I said, you don't need to know machine learning. You don't need to know computer vision. Okay, my point is that the basic ideas can be explained to you, and the quizzes will not focus on the machine learning part. Quizzes will focus on what you know about the optimization. Okay, so one of the problem in computer vision is like, let us say, 3D reconstruction problem. Okay, so there are like 2D images of an area, let us say, with the different angles. Okay, and you have taken a and this is the object here. Okay, and you have taken a picture of this from various angles. Okay, various angles, and then and this is a 3D object. Okay, let us say this is some kind of a 3D object, and then one of the goals in vision, or let us say the robotic vision, or is like you may have some kind of a drone flying around in a city and then it's taking snapshot pictures, okay, of these, and it's just taking snapshots, okay. You can say, okay, why not video? But okay, but let us assume that we only want to take some snapshots to get a rough idea of the area, okay. And the goal is to, given these snapshots with various angles and so on, reconstruct the image from these 2D images, okay. From these images, you have to reconstruct the 3D object. So this can again be formulated as an optimization problem. In this case, it's like nonlinear optimization problem, because the objective function or the loss function that we are talking about is a nonlinear. Okay, I will explain what is linear and nonlinear. Okay, so don't worry. Okay, so these are some of the applications. Like every year I try to include few things and so on. So these basic things will be there, but I might include a little bit more from other areas. Okay. It could be something from signal processing, right? So we can have one more example from there. Okay. Okay. So let us dive into optimization problem. So what we know so far, right? So what we have seen so far, what we have seen so far is, let us say, up to 10+2, or let us say in the BTech very basic courses that you may have seen in some calculus courses, or where the prof might have told you some optimization problems, right? So one of the basic forms, I have listed it here, and this itself is a solid template for you. Most optimization problem will have similar characteristics. There will be a function which we usually call a objective function, right? Sometimes it's called loss function, and depending on, sometimes it could be called cost function. So when you are working in an industry and you are trying to minimize the cost of various products and so on based on the demand, then you may call your objective function as cost function. Okay. And when you're working in machine learning community and so on, then you call it a loss function. Okay. Because you are checking the loss of your current output from your model to the actual level that you have. So that then you are talking about the loss. Okay. But a more concrete way to say is that it is an objective function. Okay. So objective function is there, and what are you trying to do? You are trying to maximize it, and you have a constraint on X. You are saying that I want to maximize this, but this is the constraint. Only within this, I want to find an X in the interval -1 to 1, where the function is maximized. Okay, so where the function is maximized. So yeah, so how one would go about solving problems like this, right? So if you have seen what we recall from our previous knowledge, okay, so we will is how we were solving optimization problems before, right? So so minimization of minimization or maximization, okay, is the minimization, let us say, of real valued function. Okay, real valued function is a function that that gives real values, right? So output is real. So for so the functions of the type R to R. Okay, R is the real number set. So this is the case here. In this case, f of x is taking x. I have not written explicitly, but it is evident from here. This is the real numbers between -1 and 1. Now we want to maximize this, right? So what we recall from our previous knowledge is that to maximize or minimize a function, what we do is that we take the first derivative, so f derivative x. Okay, so this notation means that I'm taking d by dx of f of x. Okay, so that's the short form of that. So you equate it to 0. So solve this equation. Okay, so solve for x. You solve for x, and let us say after solving you get those x for which f prime of x is 0 is, let us say, a, b, c. These are the numbers where it's 0. Then the second step is to check for the double derivative f double prime of x at these points. Okay, so you check that at x equals to a, you check that at x equals to b, and you check that at x equals to c, right? And what do you check for? You check whether it's positive or negative, right? So you check whether it's positive or negative. So then there are two cases, right? So if f double derivative of x, okay, at, let us say, a is positive, okay, so is positive, what do you do, right? So if it is positive, what do we infer from here? Right. If it is positive, then this implies that x equals to a is a what? Minima. Okay, so that is where the function is taking the minima. Okay, if it so happens that f double prime of x at x equals to a, okay, you can, same thing applies for b and c, okay, but I'm doing only one. If it so happens that f double prime of x at a is less than 0, then x equals to a is maxima. Okay, okay, so so how do I come to this conclusion here? Right, so the question is, how do I decide that this is maxima or minima, right? Well, if I draw a, so let me do it here, okay? So if I draw a plot of a function, right? So let us say this is my function f of x, right? So let us check this point here, right? So this is point A, right? So I know that f prime of x is becoming 0 here because that's where the tangent is flat, right? So this is the place where f prime of a became 0. Okay, this is the place the tangent became flat. Now we want to know whether this was minima or maxima. Okay, in the graph it is looking like it is a local minima. Okay, in the local neighborhood it is a minima. And to do that we did a double derivative test. So if we do the double derivative, what does double derivative mean? Double derivative means, double derivative is the rate of change of tangent. Okay, rate of change of tangent. Here the tangent became flat, right? But double derivative tells you, okay, tangent may be flat, but what is the behavior of the tangent, right? So is the tangent increasing or decreasing? Okay, so that's what the double derivative is, the rate of change of tangent, right? So if we look into the history here, we see that the tangent is increasing actually. The tangent is here, then it's here, then it's here. Okay, so it is in the increasing form right now. Okay, the tangent is in increasing form. So that is what this indicates. If this is the case, then it is supposed to be minima. Okay, because the tangent is because it is increasing, right? So it is increasing means it is like a minima. Okay, it's a minima, right? And then if the tangent was in decreasing form, for example, here tangent had this value, then the tangent has this value. Okay, and then tangent has Okay, sorry, let me, yeah. So tangent has this value, okay, and then tangent has this value, and then tangent has this value, and so on. So in this case, the tangent is decreasing, okay. So tangent is decreasing in this case, okay. So this is the decreasing. So if the tangent is decreasing, in other words, if the double derivative of the function is decreasing around a, okay, so this is some other point, let us say b, right? If it is decreasing, then it must have been maxima. If the tangent was increasing, then it must have been minima. Okay, that's what these say. So this is something we recall, okay, from calculus, right? So from here, from using this, we can now solve this problem, right? So by using this, we can now solve this problem. So how do we solve this problem? If we take first derivative, right? So if we take first derivative, okay. So let me clear this so that I can have some space to derive this, okay. Okay, so let me derive this now. So first, the first step is a derivative. Okay, so f so this is how much? This is minus 2x plus 4. Okay, the derivative of f of x with respect to x is this, and we have to find the critical points, right? So critical points, so these are called critical points. The points x for which f prime x is 0 are called critical points, right? So this is the step that we have to do. So critical points are found by equating f prime x equals to 0, which means that minus 2x plus 4 is equal to 0. This means that x equals to 2. 2 or, yeah, 2. Okay. So, yeah, I think I have, let me choose something bigger here. Otherwise, there is a typo, it seems here. Let me
Otherwise,
increase.
sir, we could for all the critical points, you could like minus infinity to all the critical points. Like suppose there are A, B, C critical points. So minus infinity to A to B, B to C, and C to infinity. You could find the slopes, and according to whatever the range is given to us, we can just put the, according to that we can do. So it will come out to be 1, because from minus infinity to the slope is positive, so we can see the higher end of the range. Is it?
I mean, here my goal is to show the the constraint optimization problem. So I want to also show these cases where we have this constraint on x. You could have taken this as unconstrained problem in the sense that you allow x to be any real number, okay. But just to fit this, since I found one critical point which is 2, so and I want those critical point to be within the constraint to make it interesting, that's all, okay. So this is our 2, okay, and this is where now this doesn't say it's minima or maxima, okay. That's what we said here, because unless we do the double derivative test, now we can say that it is a critical point, okay. Whether it's a maxima or a minima, we don't know. Okay, this is where the tangent is becoming flat. So tangent became flat both at minima as well as at maxima. But that doesn't say whether it was a maxima or a minima. Okay, so the places where tangent becomes flat are called critical points. Okay, so these are for the moment only critical points. Now we have to verify with the double derivative test. So this was the first step, and the second step is that you have to do the double derivative test, right? So if we do the double derivative, which is f double prime of x, so we do one more derivative of this because this already first derivative is done. So we do one more of this. So what do we get? This is negative 2. And this is negative 2 regardless of x, because there are no x left here. So this is true, this is negative less than 0 for all x in -3 and 3. Okay. If there were x left, then it would have been a little bit more interesting, because then you would have checked whether it's negative in this or not. Okay. In this case, it turns out it became very simplified. So this is less, and in particular, it is less than 0 at x equals to 2, which is our concern right now. So f double prime of x at x equals to 2 is negative. Okay, so this implies from the second derivative test, it is supposed to be maxima. Okay, so this implies x equals to 2 is maxima. Okay, so this is what you will report as an answer to this problem. Okay, so this is something we are taught in some classes. We are taught these things in calculus. Sometimes you will see in 10+2 or 10+1, but we tend to forget until we use it. So this is called second derivative test. There is a case that is left out here, is like neither greater than 0 nor less than 0. What if f double prime of x becomes equal to 0? Okay, so that can happen. Okay, that can happen, that we may have this. So then we go for a higher order test. Okay, so triple derivative and so on. Okay, and these are the places where we also encounter saddle points, but those things will come later. I will define those things later. Okay, but so far this is what we know. Okay. Okay, so what is an optimization problem? Optimization problem looks like this. Okay, so this is something I have given an example in the previous slide, and now I have written this more compactly. Okay, so this is a very compact form. I want to minimize some function and subject to some constraint. All optimization problems are like this. There are exceptions, as I said. If you move into some min-max problem, then they have a different formulations, but many optimization problems are like this. There are many things hidden here, obviously, right? Nature of the function. If you think of machine learning type stuff, then this is highly complicated neural network, right? I mean, it's a loss function of the loss in a neural network. Right? It's a loss function of the neural network. And yeah, so it depends on in the context that you are in. What is the nature, right? So as I said, in a neural network, you're dealing with nested functions, right? You do linear activations. You do linear combinations, okay, then activation, then linear combination, then activation. You do this so many times, so it becomes a nested function, which is very complicated. Okay, so and then you define a loss for that. So function f can be like variety of types, very high dimensional. Okay, x can be x can belong to some, let us say 1 million. Okay, this may be a very high dimensional thing. And previous slide, if we see, what we have done is that we have used gradients, right? So we have used gradients. So this is called gradient, like the derivative. Gradient is a derivative, but it's for on the higher order. You can think of that as higher order. Okay, there is a fine detail between derivative and gradient people talk about. Okay, but okay, I will explain those things later in higher dimensions. Okay, there is some nuance. Okay, but essentially what you have to do is to take derivatives. So if it becomes very large, high dimensional problem, you have to take derivative with respect to this very high dimensional factors. Okay, so then things become challenging. Okay, now things are like nonlinear. If it is like nonlinear, Okay, if it is 1D and nonlinear, then like this is a 1D problem, right? It is nonlinear, but since it is a 1D, there was not a big issue here. Okay, but if it is even in R2, if we have a surface, right? Okay, so if we have a surface like this, right? So this becomes a function of xy. Right. Now even the derivative is the gradient will become a vector, right? So del f by del x and del f by del y. Okay, so this becomes your gradient. And then if you do the double derivative, then it becomes a Hessian. Okay, I will do these things later on. Okay, I'm just doing the overview today. So don't worry if you are missing few things. So if you do the one more derivative, then it will become a Hessian. Okay, so you see the things, the complexity that we have, and here we had only two-dimensional vectors, right? So we had x, y, okay, which is in R2. It's a two-length vector we are talking about, but moment it grows into big ones like this. Now see, your gradient vectors are very big. Your Hessian is this million times million, right? So you are dealing with very big size problem, and big data problems like machine learning are like that. You are dealing with big data sets, right? High dimensional models and so on. So these are the challenges you have. On top of that, it is non-linear. So non-linear means that it's allowed to just wobble a lot. Okay, and this wobbling is happening in higher dimension. So that's even worse. On top of that, you add the non-smoothness, right? So non-smoothness means that wobbling is there, but sometimes not smooth. And then, so sometimes you have a corner where derivatives is not well defined. Okay, sometimes it is smooth like this here. Sometimes it's sharp. Okay, derivative is not defined here, not defined here. So complexity can go to a variety of levels. Okay. Another complexity can come from the constraint itself. Okay, so what type of constraint you have? Whether you have a convex set constraint, whether you have a very arbitrary constraint, constraints with holes. Okay, this is a nightmare. Okay, like all kind of constraints we can think of, right? Simple ones that people talk about are like cubicle constraints, let us say. So your data that you are fetching is some spherical data. Okay, it can happen. Okay, the data collection that you are doing is sitting on some nice manifold. Okay, so by manifold I mean some nice structures that you have, like sphere is a manifold. Okay, and your data, your xy data is lying here. Okay, because this is convenient when you in your data set collection, and your function is defined over this. Okay, so this is your fxy. Okay, so your constraint set is this, right? So you are saying that, okay, my x should be in the sphere. Okay, should be in the sphere. And here I want to minimize my function on this. So let us say some x star y star is there. And you can say here I want to minimize, right? What is the problem? Problem is you may be using the gradient method. Okay, but the problem is of how you go around these domains, right? Because this is now a sphere. If you do RNR, you freely move around, doesn't matter. I mean, there is a fundamental problem here of the vector space itself. The Euclidean spaces doesn't constrain you. Okay, the Euclidean spaces doesn't constrain you. I can add vectors u plus v. Doesn't matter where it leads to. I'm still in Rn. Okay, here if you use the usual vector space thing, one vector may be here, another vector may be here, but the sum is outside your sphere, outside the constraint. A disaster. Okay, because your goal, someone asked you to solve this optimization problem within the constraint, and you went out of the constraint. If you are working with real line, things are manageable. Things are not manageable when you go into higher dimension. That's the real challenge. Okay. So to solve problems like this, we have two things in our hand. Again, I'm jumping the gun here because today is like an overview. Okay. So you can just see the overview. Okay. Not all the overview. Again, I don't have time, but just some intuition. Okay. So you have a constraint, right? So then without describing too much, one can solve problems like this using Lagrange multiplier. There is a very beautiful theory behind this. You will see some nice ideas being used, and how actually they came about finding this. Some historical context I usually like to give. Okay, and then another possibility is that you treat this as it is in the sense that you take the structure into account. What do I mean by that? Of course, structure is also taken into account here, but more explicit structure you take into account. You treat this as a manifold. Okay, so there is a nice theory on manifolds. Okay, so you can do a Google search on manifold. Okay, you will see some books on. Okay, so you will see some books on like differential geometry. I'm not going to do this in this class, okay, because I don't think you have done these things, okay. But what I'm saying is like some of the research that people are doing is also in this area that we will not cover in this. Sometimes I teach optimization on manifold course, and that maybe next year, if you feel interested, you can do that. Okay, so there are two possibilities. What we will do in this course is Lagrange multiplier, where we will it gives you a general technique while remaining in the Euclidean space. Euclidean space means the flat space. Okay, flat space with no end. Okay, flat spaces where you are allowed to add vectors without getting into the trouble of getting out, falling over, whatever. Okay, but to treat some special manifold structure like this, there is a different area that people work on. It's called manifold theory on manifold. So what does this area do? Well, the main thing about this area is like how you move around these things so that you don't fall. Okay, so for example, the shortest distance between 2 points on a sphere is not really a straight line because you are not allowed to go inside, right? So that's the problem, right? Your x and y is defined only on the surface, right? So here I have x and here I have y. The 2 points are there, and this is a sphere, right? So this is a sphere. So the shortest point is not really the straight line joining this. That's the problem, because my x and y are only defined on the surface. Okay, it's like you are on the earth, and someone tells you that, let us say you are on in Hyderabad, and some of you are in, let us say, some other part of the world, let us say New York. Okay, and someone tells you what is the shortest distance between this. In the Euclidean domain, shortest distance is the straight line joining. If you follow the straight line, then you have to go inside the earth, right? Because earth is a sphere. But since you are on the earth, you have to follow the surface of the earth, right? So then it will be a geodesic like this. So if you have traveled by flight, especially the long distances, let us say you want to go to New York from let us say from Berlin. Okay, Berlin in Germany, right? So I have done that sometimes. So what I would see in the tracker in the flight, if I track, they will go via Canada and so on. Okay, so the flat it looks like this, right? And then you have the America, and then you have Europe here. Okay, and then you have like, let us say, Canada here, and then USA here. It goes like this. That is the shortest actually. Okay, because it's following the some kind of like geodesic. Okay, it could be, yeah. So for them it's the shortest. Okay, so it's not necessarily like always the they have to follow the geodesic. That's the thing. Okay, so that's one area which is coming up a lot, where you do optimization on manifold, and the reason why it is effective, especially if you have a structure. Obviously, if someone gives you a very arbitrary constraint that has no nice structure, like a sphere, like something else, like, I mean, it could be very abstract. Okay, manifolds, like if you see the Grassmannian manifold, it's like space of all orthogonal matrices and so on. I mean, rank K matrices and so on. Okay, so those are like special kind of Stiefel manifold and so on. People have derived all the tools needed to move around such manifolds. Okay, so so obviously the constraint set should be a nice one, so that some of the existing tools that people have developed can be used. If it is a very arbitrary one, no hope. Okay, so that's yeah. Okay, so this is the basic form of the optimization problem, where f of x is called objective function. I told this even earlier. Okay, and this is the constraint we have, subject to x belongs to C, right? So this will be, naturally, this will be called constraint set. Constraint set, objective function. These are the things you have to remember. Since there is an optimization method course, this will be used a lot. Okay, there will be many terms actually introduced. So you have to make sure that you revise this and know these terms. Okay. Okay, what do we want? We want to find an x such that fx is minimized for this problem. Okay, so this is the optimization problem. Objective, what are the objectives of this course? To learn, to model. Okay, so to modeling is also an important component of this course. Someone gives you a problem. How do you model that as an optimization problem? Okay, so in the recent times, you have seen that people are having a lot of success in image recognition and let us say language translations and so on. Even like proposing models that can play games and so on. Okay, all this are, at the end of the day, it's a modeling problem. You model it, and eventually it's an optimization problem. Okay, so how you model a problem. Okay, that's one thing. Okay, so you find a suitable objective function. What is the suitable objective function for your model? Okay, what are the constraints that you have in hand? And then the second part, okay, it's not necessary that both parts will follow separately. They will be mixed. Okay, so some we will do modeling and then solve it, then modeling, then solve it. So it will be a mix of this. And then we have to know, once the model is built, how we will solve the problem, right? How we will solve the given problem. So solvers are needed. As I said, the problem can come in a variety of shape and sizes: linear, non-linear, non-convex. Okay, constraint can be convex, non-convex, and so on. Dimensions can be different. Okay, so there are wide variety of solvers, and this course, after this course, you will know which solver is a good solver for the problem you have in hand, regardless of which area you are working in. Okay, if there is an optimization problem needed, then you will have a fairly good idea of solvers. Okay, and why the modeling was done the way it was done. So to get a good solver, you need to know the parameters involved in your model. What was the type of your function? What was the time? What was the dimensions over which the function is defined, and so on. Okay, so you need to know that, and then you propose a solver. So as I said, optimization is nothing but problem solving, and this is something we have been doing actually since our high school. Let us pick up some problem from our high school so that we will realize where we needed optimization. Okay, so problem is the following: of all rectangles of area 100, which has the smallest perimeter? okay, which has the smallest perimeter of all the rectangles of area 100, which has the smallest perimeter. And the question I'm asking is, how do you model this problem as optimization problem? If you indeed model your problem as optimization problem, what is the objective function? What are the constraint set? What is the final optimization problem that I am supposed to solve? Right. So let's solve this problem. We have done this, but maybe we have not seen this as an optimization problem before. We saw this as a set of tools that we have to techniques we have to follow and then just arrive at the answer. But knowing this modeling, as I said, is very important, because then you will learn to model things in different context. Okay. There are all kinds of things people are doing. Okay, so in the institute, if you are a research student, you will see that optimization will be there in almost all the things regardless of the lab you are joining. Okay, so that's the thing. Only thing that will differ is, like, if you're doing an application part, then you will be involved in the modeling aspects. Okay, so the supervisor may ask you to, oh, look, this is the application, this is the thing. Let us say I have like many drones, and then there are recharging stations and so on. I want to keep maximum of the drones in circulations, right? And I don't want to congest the battery charging machine. So what is the optimal way to do that? Okay. While there should be enough robots around, drones around so that the work doesn't stop. It is an optimization problem, whether you believe it or not. Okay, so variety of problems will be there. So let us solve this problem. Let us not go too far. Let us solve this problem. Of all the rectangles of area 100, which has the smallest perimeter? Okay, so how? First of all, draw the rectangle. Let us start with some hope, right? So let us draw some rectangle. Okay, I hope it's a rectangle. Oh, there was a rectangle here. It's not a rectangle, but square. Is it? Oh, it can work like a rectangle. Yes. I tend to use another PDF annotator, but today I had some issue in opening the file because I wanted to use another. Okay. Sorry. I have to delete this. Yeah, so I am more comfortable with the other one, but I'm using this because. Okay, so let us say we have the rectangle here. Okay, and let us say the rectangle length is x and width is let us say y. Okay, x is not equal to y because it's not a square. So what is this? What are the information we have in the problem of all the rectangles of area 100? So area is there. Area is given to us, right? So area is 100. So area of a rectangle is x times y, and this is 100. Now the question is which has the smallest perimeter, right? So perimeter is the sum of these length, right? So that's the perimeter. So perimeter of a rectangle is 2 times x plus y. So perimeter we know. So if we try to write down the optimization problem, because it is asking for the smallest, so it's like a minimization of the perimeter subject to the area is 100, right? So we can now write down, it is not yet in the full form. So let us write, but this is how we do. We go step by step, right? So what we are supposed to do is minimize the perimeter. Perimeter is 2 times x plus y and subject to area being 100, which is xy is 100. So this looks familiar. Okay, this looks familiar to what we have seen before. This is how the optimization problem does look like. Minimize f of x subject to some xy, something on xy, some equation on xy is some constraint is satisfied in xy. Okay, and this is what we have. The problem in this case can be reduced. Okay, reduced in the sense like I am given an equality identity xy is 100. So I can remove y and I can make it, for the moment, it's a function of two variable. Okay, so our objective function is like f x y. Okay, and the constraint for the moment, it's a function of two variable. Okay, so our objective function is like f x y. Okay, and the constraint set c is also a function of x y. But using this equality, we can reduce this to single variable case. Okay, we can reduce this to single variable case because y is 100 by x. Okay, so y is 100 by x. So let me solve this problem here. Okay, so now I get an idea of what we are trying to do. So first copy what we had before. So 2 times x plus y and subject to x y is 100, right? Now we can transform this to so this is a two variable problem. A two variable problem is obviously a little bit we believe that it is tricky and we don't have any tools yet to solve the two variable problem. What we know so far is one variable case, right? So but in this case it is easy to transform to one variable case. So by choosing y equal to 100 by x, so then the problem becomes 2 times x plus y is 100 by x. Okay, and now x, there is like x becomes free because y I have substituted, right? So now I can solve this problem over x only. Okay, now I can solve this problem over x. So if I solve this problem over x, so this is a real valued, so this is just a function of x. Okay, so now I can solve this. There may be certain values of x that may not be suitable because x is a positive number, right? Y should be positive because these are length of the rectangle. So those things we will find out. Okay, we have transformed this into kind of unconstrained problem actually. But if it goes beyond our original thing, we will fix it. And that's the idea. I mean, that's the good thing about real valued problems and so on, right? But if you are in a very high dimensional problem, it's not so trivial, right? Yeah, we will see those things. Yeah, that's the objective of this course. So let us first focus here. So this is like f of x. So now what did we do? We have to find the critical point. So f prime of x is what? Okay, so f prime of x is, if we take the derivative of this, so 2 remains and then 1 minus 100 by x square. Okay, so these are the derivative things you may recall your calculus. Okay, these are basic derivative and things that you need. Okay, and this has to be equated to 0. If this is equated to 0, this implies what? X square is 100. All right, so this implies x is plus 10 or minus 10. Minus 10 is rejected because this is the length of a square, length of a rectangle that cannot be minus 10. Okay, so this is the off thing that we got because of converting this problem into unconstrained problem. Okay, but that is something we can avoid just by looking into the common sense, right? Okay, so x equals to plus 10 is there. Now we have to check whether the double derivative of this, right? So let us check f double prime of x is how much? So this is 2. Okay, and well, the first term becomes 0, right? Because this is a constant, derivative of a constant 0, right? And then how much? This is like plus 2 because the 2 will come. Okay, and times 100 by x cube. Okay, I hope you remember these things. Okay, Okay, because the derivative, what we did is derivative of -2. So derivative of minus x to the -2 is -2 x to the -3. -2 become +2 here. Okay, so this is what? This is like 400 by x cube. Now we have to check at the critical point, right? So this is our critical point, right? So we have to check at critical point whether it's positive or negative. So f double prime of x at x equals to 10 is positive. Okay, so I can directly write is positive. This implies, so if it was positive, then x equals to 10 is a minima. Okay, and that is what I mean. X equals to, at this point, the perimeter is minimum. Okay, that's what we found. At this point, the perimeter is minimum because we were always minimizing the perimeter. Okay, we were asking where the perimeter is minimum, right? So at x equals to 10, we are getting the minimum perimeter. And what is the corresponding y? Well, y was 100 by x, so this is also 10. So what this says is that for rectangle of a given area, okay, for all possible rectangle of a certain area, square, because x is equal to y now, right? Square has the least perimeter, right? Square has the least perimeter. So I hope you can fill this this question. Okay, this question about what is objective function. So we derived this constraint set. What was the constraint set, and what was the final model that you derived? Okay, so all this answer is here. Okay. Okay. So as I said, optimization is nothing but it's an art of problem solving. Okay, problem solving also requires coding and so on. So those things you do data structures, algorithms, and so on. So that's also, if you do competitive programming or whatever, you have seen, right? You're given a problem, you have to model it, right? So modeling becomes very important. Actually, in competitive programming, students who do well, okay, there is a good news that from IIIT again, there is a team going. So in Moscow, but due to this current situation, they could not participate. But these guys are not just good in coding; they are good in modeling also. Okay, so modeling plays a very important role. So modeling, it means like you should be good in maths. I mean, sorry to say that, but that's, to put things bluntly, if you want to be a good data scientist or problem solver, you have to be good in maths. Now, one can say that which maths, right? If you are data science, then you have to have good maths of calculus, probability, so on, linear algebra. If you want to do only, let us say, some particular area like transportation problem or something, you can get away with graph theory, okay, all those stuff. So, but then again, you have to know how to model a problem. So the students who do well in competitive coding in the international level, they are very good in maths. Okay, so let us complicate a little bit. Let us make things a little bit complicated, still in the sense of modeling things and solving it, right? So there is a lot of text here I have put. I'm sorry about that, but let us read it anyhow. So the problem says the following. Suppose you want to reach a point A. Okay, so in the figure you can also look sometimes in the figure to see what. So suppose you want to reach the point A. Okay, point A that is located across the sand from a nearby road. Okay, across the sand from a nearby road. Okay, so the road is this part. Okay, so this whole thing is the road. Okay, this whole thing is the road. I'm going to delete this because there is a blue also. Okay. Okay, so you get the idea. Okay, the whole straight thing is the road, and this part is the sand. Oh, sorry. Okay, so this part is the sand. Okay, this part is the sand. Whole thing is the sand. Okay. Okay, so so suppose that the road is straight. So road is straight here, okay, and B is the distance from A. B is the distance from A. So B is the distance here. So B is the distance here from A to the closest point C on the road. So basically it's a perpendicular to this. Okay, so you draw a perpendicular because perpendicular will be the shortest distance. Okay, so coming back from the manifold, we are on the flat space here. Okay, so I mean locally we are flat, we are on flat space. So we can think of a straight line, okay, from point A to point C. Okay, and let V be your speed on the road. So along the road, your speed is V, and let W, which is less than V, okay, be your speed on the sand. So if you start walking on the sand, then the speed naturally will be less. In sand, you have a lot of friction, right? So you will walk with some speed V, so some speed W in the sand, okay. So right now you are at point D. Right now you are at point D, which is at a distance, which is a distance A. Okay, which is at distance A. So this whole thing is A from C. At what point B should you turn off the road and head across the sand in order to minimize your travel time to A? Okay, look here, I have not told you explicitly V and W and B and A, right? You can say that information is not complete. Well, that is just a minor thing here. What is most important is the modeling part. Solve we can do because once A and B can plug in the data are done, right? Obviously that A and B will play a role where to take off and so on, right? But let us see the thing here. So the question is, how do you model this problem, right? So this is a modeling problem right now. What is the objective function? What are the constraints? Okay, what do you want to do here? Okay, so that's the problem we are dealing with here, right? So what do you do, right? What are you supposed to minimize first of all, right? So your remember in the previous problem we said okay perimeter, right? And that gives us an initial hint directly. Like the first step itself, it tells us minimize. What was the previous case? Perimeter, right? And here what we are asked is minimize your travel time. So it is also like minimize some time, hey, the travel time. Okay. Okay. And maybe there are some constraints, subject to some constraints. Okay. Okay. So how do we model this, right? So we know it's a travel time, but how do we write the objective function? Okay. So that's the part we are interested in, right? So let us try to solve this problem. Okay. So let us go to this slide, try to solve this problem. Okay, try to solve this problem. Let us say, and another question, the model that another thing the model is asking from us is at what point from C, okay, at what distance from C before C we have to take off, right? So we are going like this, and then at what point we take off and go the sand, because that is beneficial because we will reach faster depending on the speed on the road and speed on the sand. Okay, so at what point we take off? So let us say the point is X. Okay, so the point where I plan to take off is X distance from C. Okay, B is the point at which I will take off and move towards the sand. Okay, remember this is the sand and the speed is W here and the speed is V here. Okay, and remember that our minimization problem requires time. right? So somehow we have to bring in the time thing, right? Somehow we have to bring in the time, right? So what are we given? We have a distance, we have the speed, right? So we have distance and we have speed. So which are the distances we are talking about? The distance dB is a minus x, because remember the whole thing was a. And BC is x. Okay. But and what is also given is AC is B. Okay, this PDF annotator is not very smooth. Next time I will change this. Okay, the writing is not that smooth. Usually writing is like almost like a paper, but this PDF annotator does not recognize the writing very well. Okay, anyhow, we will change it in the next class. Okay, so we have like 10 minutes. Okay, let me do it. Okay, so we have knowledge about the distance, and we have knowledge about the speed with which we can go. And what we are interested in is in traveling the distance dB plus BA, the distance we want to travel, distance or the path we want to travel. Okay. Only thing is that we don't know for which value of x, right? That's the given problem. So what do we do? Distance is known, speed is known. Okay. So time can be found. Okay. So from here to here, time I can find because distance and speed is known. And from here to here, I can again find the time because speed on the sand is given to me. Oh, okay, but what about the distance? BA. BA is how much? Well, our very old familiar Pythagoras theorem will come into play. BA is x square plus b square. So BA is x square plus b square, right? So now the distances are known and speed are known. So the total time in this case is, so let us say T1 be the time to cover dB and
so
T2
BA will be square.
Which one?
BA will be square root of x square plus b square.
It will be square root of x square plus b square.
Yeah, okay, thanks. So this will be square root. Yeah, so that will be square root. And then T2 is the time to cover BA, and the total time, the travel time we are talking about is the sum of these, right? So the travel time is okay. So let us write down now. So T1 is what? So what is so speed is distance by time, right? So time is distance by speed, right? So time is distance by speed. So T1 is a minus x by the speed on the road is v, plus T2 is, and then the thing that we have here, square root of x square plus b square divided by the speed on the sand, which is w. Okay. So this gives you the objective function, right? So that's the objective function, and that's it, right? It's an unconstrained problem here because there are no other constraint for us. Now the only thing is, yeah?
we might need a constraint that a should be x should be less than a.
X should be less than a. Yes. Okay. Yeah. Actually, yes. X should be less than a. Good. We have constraint actually. So let us write down the overall. So this is our objective. Okay, so a minus x by v plus square root of x square plus b square by w, and subject to x. Obviously x is like greater than 0. Like, okay, we want to really put it in a concrete way, then is less than equal to a. So this is our constraint. Okay, so this was the modeling thing. Now, moment someone gives you w, okay, so the things that are not known to us was a, v, w, b. Okay, so once this is known, we can solve it, because this will become a one variable problem, because this is, at the end of the day, this is still a one variable problem, because only variable is x, right? And constraint we can handle. First we'll find critical point. We will see whether those critical points are here or not. Okay, and for those critical points, we will check the double derivative and so on. So we can do this once the a and b variables are known to us concretely. Okay, so this was so what I'm trying to say is, like, modeling itself is a very fun. Okay, in fact, you become a very good sought after person when you can develop a problem solving mindset. Like, you can model problems. Okay, and these things comes with a lot of practice and so on. So what the world is looking for is a problem solver. Okay, problem are there. I can give you hundreds of problem, but only those who do well are the ones who actually model the problem well, and then only modeling after that you can solve, right? So zillions of problems are there in the world. So what is missing is the model, how we model it so that we can solve with the current tools. We are not talking about building new maths, right? Those are, let us leave it for the mathematicians. These calculus things, derivative, all this are the tools we have to use that. Okay, but we have to build our model in a way that we are in a position to use these tools. Okay, let us move on. So now you can fill this thing. Okay, this problem. Problem on daily basis could be very simple problems, like, let us say, consider the temperature data of a city in a day. Okay, so let us say at 9 a.m. the temperature is 15, let us say, in Hyderabad. Okay, which is usually like this in Hyderabad. These days, actually, in Hyderabad, it's very much cooler here. Okay, so it's maybe 27, 28 max here. Maybe in other parts of India, it's still 34 with humidity and so on. Here it's raining a lot. Actually, it's cold here. I never need this fan or anything. Okay, so 11 a.m. let us say the temperature is 30 and so on. So there is some kind of pattern we see during the day. Okay, it rises around 2 or 3 and then it starts dropping in the night and so on. Right, so this is the temperature pattern we have. Okay, so then someone may ask you, okay, tell me the temperature at 230, okay, which is not seen in your data. Okay, so 230 is here, right? So 230, 1430. Okay, this annotator is really bad. So so this is a prediction problem actually. Okay, a very simple prediction problem, and this is a data-based problem. The previous problems that we have seen is not really data-based. Data is like, I mean, there is some information was there, like how far you are from the sand and so on. Okay, but this is more like a data science problem. Here some data is given to you. Okay, some observed data is given to you at many samples. Okay, many times, durations, and so on. And what you're supposed to do is a prediction. Predict temperature at 230, and this is not yet recorded. So it's a prediction problem, and hence you have to find, first of all, a model that can do that can understand the pattern of the temperature. So it will be some f xy, some function, and that will try to understand the pattern of this data And then once the pattern is learned, in that the variable, I will put 230 and then it should produce the prediction. So for instance, what we are thinking is that at 230, which is somewhere in the middle, since we are talking about some realistic scenario, right? We are not thinking that at 230 the temperature became 0. I mean, such drastic changes don't happen, right? Things smoothly increase and smoothly decrease. That's the observation we have, and that is what model is trying to predict. Okay, so the way model is trying to predict is something like this, the temperature pattern. So this is what we want to learn. We want to learn a function that can do this. Okay, so I don't think and so since today it was a first class, so I had to spend some time on the logistic part. So I may have to stop here. So I will put some concluding remarks. So we will continue with this. Okay. So here also the modeling is needed. The modeling is needed to come up with the prediction function. Okay. And then obviously what the user is asking you to do the prediction task. But first you have to find a model. And how do you find a model? You find a model via optimization method actually. Okay, again, it will turn out to be some min-max problem, and then some constraint would be there. Okay, and then you will solve for that, and that will give you the model. Okay, so that will give you so previous examples that we have seen, we were finding the minima of a function, but here actually we are finding the function itself. We are finding the good function itself. Okay, but the way we will formulate it, it will be a minimization problem. Okay, and the minimization problem comes in the sense that we will define some loss function, and the loss will, so we will have function with some free parameters and how far it differs from the actual temperature, and we will subtract that, and that will be our abstract model. Okay, so we will see this, and this is something we will do a lot also. So I hope things were smooth. I hope there was no lag or anything. Sometimes there is the case. This video is recorded, so you will find this video and the PDF slides both uploaded by tonight. Okay, so and you will find this on the files tab of the general tab of the Teams. Okay, so both I need some time to do the cropping sometimes of the video, and that sometimes takes time. So it will take maybe a couple of hours to upload this. Okay, today there was no quiz, but there may be quizzes, as I said. Okay, it will be random. I'm not sure next class will have quiz or not, but it may be. Okay. Okay, thanks. And you may have some other class, so I'm going to stop. Sorry. Thanks. Bye. We may have tutorial also. Okay, so we will see when to do tutorial. We have not decided yet for clarifying the doubts. Okay, thanks. Bye.